So, another important parameter that is critical for internal combustion engine is the fuel air ratio or the air fuel ratio. So, as it indicates, like we have to essentially determine what is the ratio of fuel and air in a mixture of them, right. So, that is what is specified by fuel to air ratio. And before we go into defining some parameters, we are going to define what is called as a stoichiometric fuel air mixture. I am sure we would have encountered this word sometime before, right, in basic chemistry, right. So, a stoichiometric mixture is a chemically correct mixture. In this case, what is a stoichiometric mixture? It is a mixture of fuel and air that has just enough air for complete combustion of all fuel in the mixture is what is called as a fuel air mixture. Okay. So, what do we mean by complete combustion? All the hydrocarbon should be completely oxidized to H2O and CO2. Okay. So, that is a perfect fuel air mixture, okay, a chemically correct fuel air mixture, or what is called as a stoichiometric mixture. Okay. So, this is a chemically correct fuel air mixture. Okay. Now, we can have more fuel in the mixture than the chemically correct mixture. Okay. That implies what is called as a rich mixture. So, a rich mixture is one which has more fuel in the fuel air mixture than the chemically correct mixture. So, if you have less fuel, we have what is called as a lean mixture. Okay. So, these are some terms, and based on these we are going to define some parameters called the equivalence ratio phi, which is the actual fuel to air ratio to the stoichiometric fuel to air ratio. Okay. So, that is a definition, that is a definition of equivalence ratio. Some people will use another parameter called excess air ratio. It is just the inverse of this. So, it is the actual air fuel ratio divided by the stoichiometric air fuel ratio. Okay. So, that is another definition. Okay. So, you just swap the ratios. Okay. First case it was fuel to air, now it is air to fuel. So, why would some people prefer this? Because typically, like even if we consider a typical fuel where let us say the stoichiometric fuel to air mixture should contain 1 part of fuel and 15 parts of air, the fuel to air ratio will be 1 by 15, the air to fuel ratio will be 15. So, some people find it convenient to say okay, like 15:1 or 14.2:1, right, and so on, right, rather than saying 1 by 15:1, right, 1 by 15 goes into some decimal places, and so on, right, which is what to say, which people and people find more convenient to state the air fuel ratio, but both are the same, like, so it is just a matter of convenience. So, a rich mixture implies the equivalence ratio is greater than 1 and the XSR ratio is less than 1, right. A lean mixture is one where the equivalence ratio is less than 1 and the XSR ratio is greater than 1. Okay. So, that is the definition of equivalence ratio and XSR ratio. So, one more parameter which we are going to encounter is the calorific value. So, we have already encountered calorific value when we defined the efficiency terms, right. So, what is the calorific value? So, the calorific value of a fuel is the thermal energy released per unit quantity of the fuel when it is burnt completely and the products of combustion are brought back to the initial temperature. So, that is what is the calorific value of the fuel. So, it is indicative of how much what to say energy, right, heat chemical energy, the heat energy that you can get by burning the fuel, right, by combusting the fuel. So, these are some parameters that are used for quantifying engine performance. Okay. So, the next thing I want to discuss in today's class is give a notion on the indicated mean effective pressure, right. So, let us derive an expression for the indicated mean effective pressure or IMEP for the air standard Otto cycle. Okay. So, that like we understand what are the parameters that affect or influence this mean effective pressure. So, just to quickly recap the air standard Otto cycle, the PV diagram looks something like this. So, this is state 1, 2, 3 and 4. So, we always need to mark the flow of the processes, right, and also some critical characteristics of each process. Okay. So, we already know that the compression ratio R is going to be V1 by V2 and that is also going to be equal to V4 by V3, and the pressure ratio which is given by Rp is defined by P3 by P2. Okay. So, that is something which these are parameters that we already are aware of. So, now let us calculate or evaluate the net work output, right, from the Otto cycle. So, let us do that exercise. So, why are we evaluating the net work output? Because that is the definition of indicated mean effective pressure, right. It is nothing but the net work output per unit cycle divided by the displacement volume. So, we can immediately see that the net work output has two components. The first component is from during the expansion process. So, in the expansion process the work which is delivered is nothing but integral from going from 3 to 4 P times dV, right. So, that is the work output, correct. Now, how do I simplify this? I use a process relationship because we know PV power gamma equals constant, right, that is an isentropic process relationship. So, this implies that P is some C V power minus gamma, right. So, I just substitute that here. So, if I substitute it here, I am going to get this. So, what will happen if I integrate? I will get C V power minus gamma plus 1 divided by minus gamma plus 1 going from 3 to 4, right. Before we evaluate, here once again I can substitute C equals PV power gamma, right. So, what will I get? I will get PV divided by minus gamma plus 1 evaluated between 3 and 4. How did I get this? Here I can substitute C equals PV power gamma, right. PV power gamma times V power minus gamma plus 1 will give me PV. So, that is what I did. So, as a result we will get P4 V4 minus P3 V3 by gamma plus 1. This I rewrite it as P3 V3 minus P4 V4 by gamma minus 1, okay. So, that is what. So, anyway this work is positive, right. So, this is a positive quantity because it is a work output term, right, during the expansion process, and we can see that that quantity is going to be positive. So, similarly if I consider the process from 1 to 2 and we evaluate this, I would leave this as an exercise. You will immediately see that if you follow a similar process we are going to get this expression, okay. So, that is the work interaction during the compression process. Obviously, you see that this is going to have a negative sign because we are providing, that is a sign convention which is used, right. Work given to the system or work done on the system is negative. So, this is going to be negative. So, consequently the net work output is going to be the sum of the two. It is going to be P3 V3 minus P4 V4 divided by gamma minus 1 plus P1 V1 minus P2 V2 by gamma minus 1. So, this is the net work output, okay. So, now we simplify. So, we know that P1 V1 power gamma equals P2 V2 power gamma, right. So, that is from the process relationship. So, we immediately can rewrite P2 by P1 as V1 by V2 to the power gamma, and V1 by V2 is the compression ratio. So, I get R power gamma. Similarly, P3 V3 power gamma is going to be equal to P4 V4 power gamma. So, this will give me P3 by P4 to be equal to V4 by V3 power gamma, and that is also equal to R by R power gamma, correct. So, this essentially tells me P2 by P1 is equal to P3 by P4. Why? Because both ratios are equal to R power gamma. So, obviously both ratios should be the same. So, if I change the order, I will get P3 by P2 to be equal to P4 by P1. And what is P3 by P2 equal to? The pressure ratio Rp. So, you see that P4 by P1 is also R subscript P, right, the pressure ratio, okay. And another equation which we are going to use here is the following. If we take P3 by P1, we are going to need all these pressure ratios shortly, I can rewrite it as P3 by P2 times P2 by P1. Okay. What is P3 by P2? Rp, right? What is P2 by P1? R power gamma, right, from here. So, we are going to utilize all these equations. Okay. So, now what we are going to do is the following. We are going to simplify this expression. So, let us take the expression for W net. Let me take P1 V1 divided by gamma minus 1 as common. So, what will I have? I will have P3 V3 by P1 V1 minus P4 V4 by P1 V1 plus 1 minus P2 V2 divided by P1 V1. Immediately we can observe that V4 and V1 get cancelled. Why? Because they are the same, right. What is P3 by P1? Let us take the first term. P3 by P1 is going to be Rp R power gamma, we just derived it, right. We can observe here, correct. So, that is Rp R power gamma, and what is V3 by V1? It is 1 by R. V1 by V3 is R, V3 by V1 is going to be 1 by R, right. So, that is how the first expression will simplify. P4 by P1 is Rp, we just got it here, right. P4 by P1 is Rp, right. I am going to substitute for that, then I will have plus 1. What is P2 by P1? It is R power gamma, we get it from here, and what is V2 by V1? Once again 1 by R, right. It is a reciprocal of the compression ratio. So, what we have is the following. We have P1 V1 whole to the power gamma minus 1 times Rp R power gamma minus 1 minus Rp plus 1 minus R power gamma minus 1. Okay. So, this is what we have. So, this implies that the net work output in one cycle is going to be equal to P1 V1 to the power gamma minus 1, divided by gamma minus 1 multiplied by Rp minus 1 times R power gamma minus 1 minus 1. Okay, I can simplify that into the product of these two factors, right. So, this is the net work in one cycle. So, what is IMEP? It is this net work in one cycle divided by the displacement volume. So, now going on, what can you say about the displacement volume? V displacement is going to be equal to V1 minus V2. I can rewrite this as V1 times 1 minus V2 by V1, and what is V2 by V1? 1 by R. So, I can get V displacement as, I can rewrite V displacement as V1 by R times R minus 1, right. So, very simple. So, I am just using the definition of compression ratio to just rewrite the displacement volume in terms of V1 and R. Obviously, the reason will become very clear shortly, right. So, that is my displacement volume. So, let us come down. So, IMEP is going to be equal to the net work done in one cycle divided by displacement volume. The net work done is this P1 V1 power gamma minus 1 multiplied by Rp minus 1 times R power gamma minus 1 divided by the displacement volume, that is going to be V1 divided by R times R minus 1, right. So, we can immediately see that V1 and V1 cancel off. So, this implies that the indicated mean effective pressure of the Otto cycle becomes P1 times R, because the R comes from the denominator, times Rp minus 1 times R power gamma minus 1 divided by gamma minus 1 times R minus 1. So, this is the expression for the IMEP for the Otto cycle. Okay. As an exercise, I want you to do the same derivation. There is find an expression for IMEP for the air standard diesel cycle and the dual cycle in terms of the initial pressure P1 and all other parameters R, Rp, Rc as appropriate, okay, and gamma. Okay. So, you can immediately see that the indicated mean effective pressure is dependent on P1. P1 is the pressure at the start of the cycle, right, the initial state 1. So, going back to our previous discussion, we can immediately see that if I increase the value of P1, obviously the indicated mean effective pressure also would increase, and the process of supercharging would essentially increase the value of P1. So, now one can easily observe the direct benefit of increasing the inlet pressure, right, and this process of supercharging is something which we will discuss in the next class. Okay. So, I will stop here for this class and we will continue with supercharging in the upcoming class. Fine. Thank you.